Hello, everyone. Welcome. This week's seminar speaker is going to be Saeed Ghoddousi, who's a PhD student in the Department of Civil and Architectural Engineering at the University of Miami. Uh, his emphasis is in architectural engineering. He finished his bachelor's in mechanical engineering at, I'm going to pronounce this badly, sorry, but Khaja Nasir Tusi University of Technology in Iran. And he has a master's in energy systems engineering at Semnan University in Iran and MSc in mechanical engineering at the University of Idaho. His research interests and areas include building mechanical systems and renewable energy systems. He's currently working on the energy model of HVAC system components, including cooling towers, chillers, pumps, and heat pumps. So, Saeed, thank you very much for agreeing to do this, and the floor is all yours.
Dr. Pranoy, thank you. And thank you everyone to joining this seminar, and also first I should say hi to everyone and then thank you for giving me this opportunity to present my part of my research in the seminar CAE seminar series. Just to make sure, can you hear me right?
Yes.
Okay. My presentation will be about the investigation of different cooling towers fan control strategies, and I will go through this presentation through the following outline. Actually, because what we are doing in our group, it's a little bit far from other students, other graduate students here I try to provide more background about what I would like talking about, and then I will go through the objectives of our work and our presentation, and also the model development, and also we will identify the optimal control method and evaluate the conventional controls, and finally we will go through the conclusions. HVAC systems that comes from the heat, ventilation, air conditioning systems. Goal is to maintain the desired indoor condition. Who provide this and what's this desired indoor air condition? By controlling the indoor air temperature between 73 to 77 degrees of Fahrenheit, and also relative humidity between 40 to 60%, based on the ASHRAE standards, we will have the comfort condition, indoor comfort condition. ASHRAE is a very big kind of association for the American Society of Heating, Refrigeration, and Air Conditioning Engineers provide these standards. And in HVAC area, our goal to control this temperature and relative humidity. HVAC systems account for around 40% of the total energy used in building. It's a very large amount. And you may see in your bills, in FEL bills every month, that whenever the temperature goes up, we have a higher temperature, outside air temperature, our bills goes up, because this is a very big part of our bills. And any work and any studies to optimize these systems will have a big impact on the also energy conservation, and also cost conservation, and also reduce the costs for the everyone that used the HVAC systems, and also the maintenance of the buildings. But how we can, but in every area that we want to control something, we have some disturbance in the systems. In HVAC system, in indoor area, we have some disturbance, and we need to control them. What's the source of the disturbance in the, for instance, indoor area, in a room? We can say people, one of the disturbance, because usually people generate heat. When we have more people in a room, we feel more, we feel high temperature and too hot. Or the electrical system inside the room, for instance, the receptacles, lights, also video projectors, also computers, any other device, any device, electrical device will generate heat, and it's a kind of the disturbance. And also the sun and the solar radiation outside the building push the system, and also it's kind of the disturbance that generates heat for an indoor area. And also the external building surfaces, because of the temperature difference between the outside and inside of the indoor area, this will provide for us the disturbance, and disturbance tries to increase the temperature of the indoor area. But what we would like to do to provide this indoor comfort condition in HVAC system is to overcome these disturbances and somehow control the temperature by overcoming these disturbances and compensate this disturbance to create this desired condition for indoor condition. But how we can make it? How we can compensate this disturbance? The question is this, and here we would like to say that we can say that the supply cold air to the any indoor area is the way that we can remove the heat, remove the disturbance, compensate the disturbance. For instance, in the summer, I would like to emphasize on the cooling load here. We say total disturbance, for instance, every disturbance that we have from the heating sources, disturbance sources from the people, electrical systems, solar radiation, and also a building envelope, anything we say is as a cooling load in summer that we need to compensate this disturbance and provide the desired condition. But the thing is that how we can provide, we found that we need supply air, right? Next step, how we can supply this cold air. We need to have a cold air, and we need to provide this cold air. How we can do that? You may pass that through the hallway in our CA department, and you can see a room that's room 329, air handler rooms. Sometimes you may have some question that what's inside this room. Inside this room, we have one important instrument component in HVAC system is air handling units. Air handling units that you can see the figure on the right-hand side, the schematic figure, and also the real picture of the air handling units is a instrument for providing supply the cold air. But how it does provide, how it provides by the air handling units. In air handling units, we have a cooling coil. In a cooling coil, we need chilled water, which goes inside the cooling coil. And by having the fan that push the air through the cooling coil, which is cold right now, and by having this fan push the air to that, we can generate the cold air. This cold air will direct to the indoor area, for instance, the room, using the duct that you can see in every single rooms that for compensate the cooling load. If a quick review, we have a disturbance, we have to compensate the disturbance, we generate the cold air. How we generate cold air? By air handling units, send it with the duct to the system, and also return the air from the room air to the air handling unit. And this cycle happens and happens again to provide the comfort air for indoor area. But the key point is that is the chilled water. We need chilled water, and how we can have this chilled water how can we provide chilled water for the air handling units. For and clarify this part, we need to go to the refrigeration cycle principle. Here we have one refrigeration cycle that every day we use it, the refrigerator. What does the refrigerator, how it can provide the cold inside the refrigerator, cold air inside the refrigerator is a key parameters. When you open the refrigerator door, you can see that the warm air naturally goes into the inside the space, cold space inside the refrigerator, and this process happens naturally. But our goal in a refrigerator is to transfer the heat from the inside, from the cold space to the outside, which is warm space. That cannot be happen naturally, and we can do it by having work input. And what's the work input and how it's done? It's based on this process, this cycle that has 4 critical components: evaporator, condenser, compressor, and expansion valve. And also the refrigerants inside the coil. We have a coils in the refrigerator, and it moves these paths. And refrigerants are which we know as a working fluid. It's can work in extreme temperature and extreme pressure, and high and low pressure. And we need and we name it as a working fluid for us. Goes this process. For instance, in evaporator, it needs heat to based on its pressure. It needs heat to change its phase, and how it can get its heat. It receives heat from the cold area, and in this area we are receiving heat from the colder. With this process, we are receiving heat from the inside of the refrigerator, cold area, and then these refrigerants goes along to the and move their path to the compressor, that you may hear some noises when when the compressor work in a refrigerator. This is a compressor that we provide for the energy to as a work input, and then increase its pressure, and then go to the condenser. Where is the condenser in a refrigerator? On the back of the refrigerator, you may see some coils. And also you may feel a warmer area in the back of the refrigerator. Why? Because here it rejects heat based on the pressure and some basic laws of the thermodynamic. It rejects heat to the warm area, and then go to the expansion valve and do this cycle again and again. What happens during this cycle? During this cycle, we direct the heat from the colder area to the warmer area by having work input in the compressor. And this is a refrigeration cycle that we can see in a very simple example that every day we use it. And every day we use it. The process to provide, come back again to the story. Our story was to provide a chilled water. How we can have a chilled water? The same process can happen with another application, which name is water-cooled chiller in a general name. And in a chiller, we provide, instead of the inside cold inside air of the inside the refrigerator, we provide the chilled water. And you can see a real picture of the chiller here that usually is installed in a, for instance, lower level of the buildings. And we will try to, based on that 4 critical components that we already have it in a refrigerator part, we will try to provide the cold air, cold water, chilled water here. And as you can see, in a return chilled water and supply chilled water, and supply chilled water will direct it to the air handling units and generate cold air and process this story to compensate the disturbance to the system. But the thing is that the principle is completely similar to the refrigerator, because it's a refrigeration cycle principles, and we have expansion valve, evaporator, compressor, and condenser. But for the condenser part, for the refrigerator, you can compare it. When we have a refrigerator, it transfers heat with ambient air, right? It's very easy. But for the chiller, we have a large system. We couple the condenser with another application, which name is cooling tower. You may see on the top of the high-rise building the cooling tower. The cooling tower system, the cooling tower main responsibility is to dissipate the heat from the condenser part to the ambient air. And this cycle, including the cooling tower and also condenser, we name it as a condensing water system. And we would like to focus more on this part. Cooling tower in condensing water system, cooling tower role is very critical. When we are talking about the condenser, which means that the vapor refrigerants goes inside the condenser and also rejects heat to the one closed loop water cycle that you can see with the red line here, and turns to liquid refrigerant. This heat is dissipated to the water, makes the water temperature, for instance, this is a standard temperature that we are talking about, that at 95 degrees of Fahrenheit of water, and also ambient air temperature surrounded the cooling towers. We try to using the fan with a specific speed that suck the air inside the cooling tower and directed it to the outside the cooling tower, right? And in this process, water temperature tries to cool down, reduce its temperature, and also ambient air temperature will heat up and it increases temperature. And this heat, in this process, heat will transfer from the water to the ambient air, right? The critical definitions that we need to emphasize here is 3 parameters. One is the fan speed. I would like to mention it that first, we are dissipating heat from the working fluid to the ambient air by using the fan speed, because by increasing the fan speed, we will change the leaving water temperature from the cooling tower that you can see. And leaving water temperature is another important concept that we need to, but we'll discuss about that in future slides. And another concept is approach temperature. Approach temperature, what's approach temperature? Approach temperature is the temperature difference between the ambient air and leaving water temperature. And we'll work with these three parameters in future slides more. Cooling tower operation, again, we show that I showed that the fan speed impacts the leaving water temperature, impacts the approach temperature. By having the higher fan speed, we are reducing the leaving water temperature. You can see in the figure that ambient air temperature is 78, entering water temperature to cooling tower is 95, and our leaving water temperature in this standard condition will be around 85. But which means that our water temperature reduced from 95 to 85, and also our approach temperature is 7 degrees, which 7 degrees is higher than ambient air temperature. Ambient air wet bulb temperature is 78 at 100 speed of the fan. If we reduce the fan speed, for instance, to 50%, we can see that the leaving water temperature increases its temperature to 90. From 95 to 90, you can see in a higher points, and also the approach temperature will be around 12. Approach temperature, again, the difference between the ambient air vapor temperature and also the leaving water temperature from the cooling tower. This fact can show that how fan speed can affect our leaving water temperature, right? And also the approach temperature. For the design condition, we have a design condition in designing cooling tower. In design condition, we need to consider the water entering temperature as a value is as a standard is a 95, and also ambient air wet bulb temperature is 78. For sure, every single time we don't have this temperature, and this will affect our system. But in a design condition, we are designing based on these criteria: water entering temperature as 95, ambient air wet bulb temperature as 78, and also the fan speed as 100 speed to maintain leaving water temperature as 85 and approach temperature at 7 temperature, right? And based on this design condition, this is a conventional way to control the cooling tower operation. In a conventional ways, in a conventional controls, we have 3 conventional controls. First, the fan speed is modulated to maintain the living water temperature at this 85 degrees, right? This is a conventional fixed living water temperature at 85. Another way is to modulate this fan speed to keep the approach temperature constant at 70. And also another is fan speed is a fixed at 100% speed, regardless of living water temperature, approach temperature, and any other. This is a conventional control strategies that usually uses in cooling towers, and we would like to discuss more about that in a future slides. We said that in a refrigeration cycle, in a chiller and a cooling tower, in a cycle of the cooling system, we need to have a work input. Where we have a work input, we have a work input on a chiller part. We said that as a compressor, like the refrigerator compressor, and also the cooling tower fan. Cooling tower fan needs a work input to work, and with the higher speed, we need more energy to provide that. But as you can see in a right-hand side on the top figure, chiller efficiency depends on leaving water temperature, the water enter into the condenser, and you can see by having a lower temperature, we have a higher efficiency of the chiller, which means that our chiller needs less energy, right? On the other hand, we have the fan speed that when we increase the fan speed to have the lower leaving water temperature, we need this speeding of the fan causes the fan power increases. And it's kind of that we need to consider all of them together to find the optimal operation of the cooling system. As you can see in the right-hand side on the below figure, that the optimal point of our cooling system will be around somewhere around 60% of fan speed, not at the highest speed or lowest speed. And this is for instance, for one condition that we bring it here, but the thing is that we are trying to find the optimal point. And based on this slide, we found that the cooling tower fan speed can affect our system optimal control, and our cooling system using the optimal works efficiently, right? Based on that, we want to provide our objective. To make a long story short, we try to control the fan speed to make our system, our chiller system, which is coupled with the air handling units to provide the air, cold air inside the area, compensate the disturbance. We want to change the fan speed to make this cooling system, including cooling tower and chiller, works efficiently and in an optimal point, right? And based on this, we have our problem statement that optimal fan speed exists for the minimize the total power input of the cooling system. And also we have some conventional control strategies that we mentioned that they may not be optimal. How we can solve these problems if we have some objective for that. First of all, identify cooling tower optimal fan control strategy based on the chiller load, based on the different ambient air temperature, based on the cooling load. And also evaluate the conventional controls with the optimal one by having the optimal one. The approach for this one, first, build up the model, total model for the cooling system, total power model for the cooling system, then identify the optimal speed simulation on a different outdoor condition and also chiller load, and also evaluate the different control strategies, the conventional one and the optimal one. We mentioned that we need an energy model for the cooling system. In a cooling system, we have in this cooling system that we have, which has 3 cooling towers, 5 chillers, 3 condensing parts, some components in it. We have 2 main energy consumer, which is fan and chiller. And we need to model both two. We can see that the fans and the chiller, to model this energy, to have an energy model of this system, of the cooling system, first we need to model the cooling tower. We can project the cooling tower. What is we are going to show you. I'm going to show you that how we can model the cooling tower. In our model, we can project the living water temperature of the cooling tower based on inputs. And 2 important inputs is ambient air, wet bulb temperature, and also fan speed, right? Based on this projected temperature, which also affects the efficiency of the chiller, we try to model the chiller. Chiller power is a function of the cooling load and this projected temperature that we will model it. And for the chiller part, we use the manufacturer real model of the chiller, how it can affected by the living water by the supply temperature of the chiller, supply temperature to the condenser of the chiller, and also the cooling load, and after that we can have our total system energy input based on these based on 3 input: cooling load, ambient air, wet bulb temperature, and also fan speed of the fan. It's good to notice here that we cannot control the cooling load. We cannot control the ambient air, wet bulb temperature. And these are independent variables in our system. But we can control the fan speed of the cooling tower. And this, we are going to optimize this fan speed to minimize our energy usage of the cooling system. For the chiller model, I said that we use the actual chiller, a real chiller, manufacturer chiller. You can see the 2,000 tons centrifugal water-cooled chiller. You can see here that by reducing the living water temperature, and also you can have a higher efficiency of the chiller. And also it's the chiller efficiency is a function of the chiller load as well. Finally, we can say that in a chiller model, we have 2 parameters that affects that cooling tower living water temperature and chiller load. And based on the real model, we have the model for the chiller. Another model we need is a cooling tower model. You can see the schematic of the simple cooling tower here. Sorry. Here, you can see that we have entering water temperature. We already said that a standard value is 95, right? And also ambient air, wet bulb temperature, and also fan speed. And we can project the living water temperature using the entering temperature, water entering temperature, ambient air wet bulb temperature, fan speed, and design moisture transfer coefficient, which is unique for every single cooling towers. Based on these 4 parameters, we can project the living water temperature. But how we can model it? We cannot see it at a one big picture. We have to go piece by piece, and we will zoom in and select one very small piece of the water that has a heat transfer with the ambient air. You can see in the right hand side that we consider one water droplet and air stream surrounded this water droplet. The cooling tower theory, if we focus on this water droplet, we can, by ignoring the thermal resistance of the interface, we can see that, okay, the interface we can write down the heat and mass transfer relationship between the water droplet and air stream. These are some kind of the technical part. I will try to quickly pass this part, but the main idea is that have the heat and mass transfer relationship between the water droplet and air stream, right? That you can see here. In order to have a total heat transfer rate, we know that the heat transfer, we can divide it to 2 heat transfer: sensible heat transfer and latent heat transfer. Sensible heat transfer driven by the temperature, and latent heat transfer driven by the humidity ratio, and also Levy's factor, which combines the mass heat and mass transfer together. These 3, based on these 3 equations, we can have the total heat transfer that driven by the enthalpy of our water droplet that we consider here as a total heat transfer that we can see at the last equation. But another thing is that we have an overall energy conservation law based on the first thermodynamic law, that the total energy released by the water, we can have it based on the enthalpy difference and also temperature difference, and the total energy received by the air based on the enthalpy difference. And we can have the overall heat conservation law for the water side, for the air side, and for the air enthalpy at the saturated water temperature that we have, right? Now we need to go to the next stage to have a heat exchanger theory based on the cooling tower energy balance that we already developed it, and using the another parameter here to have the standard differential format for the heat exchanger driven by the enthalpy difference that you can see at the last equation. We have an enthalpy, we have an enthalpy difference, not temperature difference, at the saturated moist air and also the air stream. This is a critical point that we need to work with. And by integration of these droplets that's surrounded by ambient air and also the interface saturated part, by integration then we can have the large scale heat exchanger theory. In the large scale heat exchanger theory, we have a different method to analyze it, but the one of them is epsilon NTU method, which is a epsilon number of transfer unit method, that we can follow this process, and based on the cooling tower equation that driven by the enthalpy, we can have the actual heating heat transfer, and also the most important part is that we can project the living water temperature from the cooling tower by using 4 inputs. We mentioned it based on the entering water temperature, ambient air vapor temperature, cooling tower fan speed, and the coefficients base, which is constant for unique for every single cooling towers, and we can project this living water temperature. Here we can project the living water temperature, and we have the cooling law, and also we have the chiller model. We can say that we have a total model of the cooling system, a total energy model of the cooling system. Now we need to calibrate on a real case study. We have a case study on which is a very large central cooling plant in Norman, in Oklahoma. It has a 4,000-ton cooling towers and also 2,000-ton centrifugal water-cooled chiller. You can find other specification of our system on the table on the right-hand side. And based on this calibration model, we applied our model on this on this case study, and try to find the optimal fan speed to minimize the energy usage, to minimize the energy input of the cooling system. Sorry. Okay, based on the result, we can see that the optimal fan speed is very sensitive to the chiller load, and less sensitive to the ambient air wet bulb temperature. As you can compare the right-hand side and left-hand side figures, when we change the chiller load, when we are changing the chiller load, it means that we are increasing. We have the the optimal fan speed. We need more fan speed, which means that we need a more power input to our fan. And also, we can see from the right-hand side that ambient air wet bulb temperature does not too much affect on optimal fan speed control strategy. Another strategy was the optimal living water temperatures. And for the living water temperature, we can see that in the right-hand side, the optimal living water temperature is more sensible to the ambient air wet bulb temperature and less sensible to the chiller load. And for the approach temperature that we mentioned, that it's I mentioned that based on the temperature difference of the ambient air temperature and also living water temperature, the optimal approach temperature is a function of the both ambient air wet bulb temperature and also chiller load. You can see in the both figure that how it can affects the optimal. Both of them can affect the optimal approach temperature. So by comparing these three optimal control strategies, we can find that we can have a kind of the comparison between them. First of all, we can say that the optimal fan speed control strategy is an open loop, is a simple, and because it's open loop control way, and also it is a simple way, we can in our study we can recommend this control strategy to be used in the system. The optimal living water temperature is a closed loop cycle, is a closed loop control, and which means that for instance, we need the sensors to compare the values and allow the system to run and modulate the fan speed. This process is not recommended because it's by having a small sensor error. For instance, if the living water temperature is real in 85, but it senses it as 84, only 1 degree, it will affect the fan speed and may cause to run the fan not efficiently. And this is because of we need a closed loop cycle in it. We cannot. I think that in compare with the optimal fan speed, we cannot recommend this part. Also, the optimal approach temperature is a control approach, is a closed loop control. And it has a 2 input, and we said that it has a 2 input: ambient air wet bulb and chiller, sensitive to both. And it is hard to implement in a system. And again, because of its closed loop, and it has a sensor, and the reason that we have discussed an optimal living water temperature model, we can say that this is not recommended. Finally, we can say that optimal fan speed is recommended approach to control the cooling tower fan speed to minimize the total cooling system working input. These are dependents together, because when we are changing the fan speed, we are changing the optimal living water temperature. We are changing the living water temperature. We are changing the approach temperature. These three other optimals. And these are dependent. And also, in this slide, here's the optimal power consumption based on ambient air wet bulb temperature, and you can see that total power consumption, energy consumption of the cooling system is a function of the chiller load and also ambient air wet bulb temperature. Another goal that we had, to evaluate the conventional control strategies. We mentioned that we have three conventional. First of all, is a fixed living water temperature at 85, regardless of the ambient air condition and regardless of the cooling load and anything. This strategy may cause energy waste because it's not efficient. And we can evaluate it based on our model. and running fixed living water temperature at 85, and see that by having this 85 fixed living water temperature, we may have up to 70% 70% energy loss based on the ambient air wet bulb temperature, and it is very large amount of energy loss. You cannot believe it how this method is now currently using in a cooling system. I think that most of the cooling towers, or maybe we can see that they are working with these parameters and these control strategies. This is not efficient. Also, if another conventional approach was fixed approach temperature at 7 degrees, and similar to the last slide, we applied in our system, and we can see that by the result of the simulation, we see that very big energy waste, less than fixed living water temperature, but still energy waste up to 9% of the total energy system consumption can be waste here using the fixed approach temperature, and which is not optimal. And the last conventional control was the fixed fan speed at 100%, regardless of any other inputs. And this was, we can see that up to 21% energy waste happens when we use this 100% fan speed in different ambient air vapor temperature. Another conclusion we can have from this slide that, as you can see, for the relative, for the chiller load, more than 50% chiller load, the energy waste is less than 5%, and we may be able to define one simple strategy to control the strategy, that if for instance, the chiller load is higher than 50%, we can use the constant fan speed, 100% fan speed control strategy, but because it has less energy waste when compared with the situation that our chiller load is lower than 50%. Finally, we can say that the energy model we in this study try to have the energy model of the water-cooled chiller cooling system, which is developed, and since we have the optimal fan speed is significantly impacted by the chiller load, and also the less impacted by ambient air wet bulb temperature, we can see that the optimal fan speed control is better than optimal living water temperature control and optimal approach temperature control advances from that. And also we evaluated the conventional control strategies, which was this fixed living water temperature and fixed at 85 and fixed approach temperature at 7 degrees, and found that, and also fixed fan speed, and evaluated with by comparing to the optimal one to find the energy loss using these control strategies. This is my presentation here, and I would like to again thank you for your attention for this presentation.